Yes, whenever you are back, Tariq, please.
Yes, I'm back, sir.
Yeah. So in today's class, we will talk about combination of cells, and then we will talk about the RC circuit, and then we will talk about the effect of current, and then we will talk about bulb, and then we will talk about Kirchhoff laws, right? And then we will spend this chapter. Right? So the last topic is meter bridge and potential, which is that. So let us start. So first one is the combination of. First one is the series combination. So all these cells and with its internal resistances are connected in a series. So let's say we have these cells, right? And this is connected with some external resistance. So this is E1 R1, this is E2 R2, this is E3 R3, and this is the external resistance. So in series combination, equivalent EMF, that is simply E1 plus E2 plus E3. And R equivalent is simply R1 plus R2 plus R. So current would be equal to E equivalent divided by R equivalent plus 1. So that is the case of this series combination. And let's say if the polarity is changed. So let's say this EMF is connected in opposite way, right? So we have already understood that. Yeah. So the polarity is different, and this, this is E1, this is E2, this is E3, this is R1, R2, R. So we can see that this is positive, negative, but this is negative, positive. So this is in opposite polarity. Current is flowing in this way. So this is discharging, but this is charging because this is getting current in this. So this is charging, right? So whenever the charging is happens, so then the polarity will be changed. That would be negative, right? So yeah, this is charging, this is discharging, and this is discharging, right? So then this would be how much? E equivalent would be E1 minus E2 plus E3. And R equivalent, that would be simply all the sums. And current, again, that would be same. So we have to remember that current is always this. Right? So this is the case of the series combination. And what happens when we combine these circuit with equal EMF? So let's say we have this equal EMF and all have same EMF and same resistance. Same EMF and same resistance. Up to let's say n volts, right? Not n volts, but n terms. So this is n columns, right? And then this is connected to the external resistance. So E equivalent would be how much? E1 plus E2 plus E3 plus so on plus En, which is E plus E plus E plus E up to En. So that would be how much? That would be simply N, right? Sorry. Similarly, R equivalent, that would be also NR. So your current would be how much? Current would be NE divided by NR plus NR plus R. So this is the case of the response. And then you have the parallel combination. So then you have this parallel combination. So in parallel combination, the EMF are joined like this. And this is connected to the resistance. So this is E1, R1, E2, R2, E3, R2. So for the case of this parallel combination, E equivalent by R equivalent, that is given by E1 by R1 plus E2 by R2 plus E3 by R. And 1 by R equivalent, that is given by that is given by 1 by R1 plus 1 by R2 plus 1 by R. So this is the case of the parallel combination. And same thing will happen if we have this different polarity. So then that will be different. So we can calculate the E equivalent from here. That would be R equivalent and multiplied by E1 R1 plus E2 R2 plus E3 R3. So I can write this as E1 R1 plus E2 R2 plus E3 R3, and this is 1 by R because 1 by something will go in the numerator. So this is 1 by R equivalent. So we can write this one as 1 by R1 plus 1 by R2 plus 1. So this is the E. And similarly, if we have n columns, right? So we have n columns of these equal EMF. So not n columns, but n rows of equal EMF, and in this case we have dash 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 up to this one, and then this is connected to this. So this is E R E R E R. So then what will happen to the total? So then what will happen to the total? So we know that E equivalent is E1 by R1 plus E2 by R2 plus En by Rn divided by 1 by R1 plus 1 by R2 plus 1 by R. This would be how much? E by R plus E by R, because all are equal. E by R, and then this is 1 by R plus 1 by R plus 1. So this is ME by R and M by R. So M will cancel, R will cancel. So E equivalent for the case of parallel combination, and 1 by R equivalent, that would be 1 by R1 plus 1 by R2 plus 1 by Rm. So this is M. Right, so this would be M by R, right? So R equivalent, that would be R by. So your current would be how much? Current is E equivalent by R equivalent plus R. So that is E divided by R by M plus R. So that would be equal to E by R plus MR divided by M. So that is ME by R plus MR. So that is the current for the case of parallel combination. Right. And finally, what you do is that finally the special case is that you connect in cell in series. So you have let's say ER up to n column, right? And then you have same m rows. So you have m rows, right? Then what will be the then what will be the equivalent EMF and what would be the current, right? So let us solve this. So let us solve these independently. So first there is this series combination, right? There is this series combination. So we can write this equivalently as NE, right? This is the single cell which will consist of all these EMF and then NR. So this is the equivalent single cell on these series combination. Is this clear, Tariq?
Yes, sir.
Yeah, and then we have this M, right? So NE and NR. And then these are one single cell connected to this photoresist, right? So now we can find out what is the E equivalent from this case. So E equivalent would be NE by NR plus NE by NR plus so on up to M roots, right? And then we have 1 by, let's say, NR plus 1 by NR up to M values. So this would be how much? This N will cancel, right? So then this would be then this would be M E by, and in the denominator, what will happen?
Sir, can you show the diagram?
Yeah, which diagram? This one.
Sir, this one, yes. 1 minute, sir. This.
Yeah, I will give the time to note it down. All these.
Oh, okay, sir. Sure.
Yes,
Okay, sir, I can continue.
yeah. So then what would be, yeah, so 1 by NR, 1 by NR, so that would be how much? That would be M by NR, right? So M will cancel, R will cancel, and you will get how much? So this N, this will be N. So that would be E equivalent, right? And R equivalent would be how much? So 1 by R equivalent. That is 1 by NR plus 1 by NR up to MR terms. So that is M by NR, right? That is 1 by R equivalent. So you will get R equivalent as NR by. So this is the R. So your current would be how much? Your current would be E equivalent divided by R equivalent plus R. So this is NE divided by NR by M plus R. So I can write this as NE NR plus MR divided by M. So current would be MNE divided by NR plus M. So this is the case of the different combination of series and parallel. So we have same EMF and we have n columns. So columns are these ones, n columns and m, right? Okay, so please note it down from here and then we talk about ours
Definitions.
from here, right? Whenever you want me to scroll down, please. Yeah, whenever you want me to scroll down, please.
So what is capital R? Capital R is resistance.
Capital R is the load resistance on which we are,
Load.
right? That is the load resistance.
Then what is small r?
Small r is the internal resistances of these cells, right?
Okay, sir. So capital R is load resistance and small r is the internal resistance.
Oh yeah, internal resistance of these cells. Because if you connect these EMF to its terminal, then this would be short circuited, right? You are connecting this one to this. So you're connecting the negative terminal to the positive terminal, then it will be short circuited, right? Because if you have a cell and if you connect that cell, so if you connect the positive terminal of that cell to the negative terminal, then that would be short circuited, right? So we need this load resistance to measure the voltage or voltage drop, right? We have to add some device to this cell. So this is some device that we are adding, right? Yeah, whenever you have put it down, please tip so that. Yes, sir. Noted, Tari.
Yes, I noted this.
Yeah, noted. The note it down so that we can cover this chapter.
The first one is also series combination.
Yeah, this one is also series pump because all these cells are connected. All the negative terminal are alternatively connected to the positive one, right? Whenever we combine all the positive ones to one point, all the negative ones to the other point. So that is parallel combination, right? Whenever we combine alternatingly, so that is the series combination. So this one is an example of series combination with equal internal resistance and equal EF. So these all these n columns have a same EMF and same internal resistance. Then what will happen to the equivalent EMF, R equivalent and current?
So this is the series terminal combination.
Yeah, this one is the series combination, right?
No, the series terminal combination.
Yeah, terminal one. Yeah, so series EMF combination. So combination of cells is yes, noted.
1 minute.
Chavez is one. Yes, noted, Rani.
Yes, sir. Finish, yes.
Then please quickly.
Can you show parallel?
Yeah, parallel one. This one.
Yes, sir.
Yeah, quickly note it down because we have. Yes, hello Shaved. Assalamu alaikum. Yes, we got it right. Yeah, so we are just doing the competition of things and if you guys have noted it down, please quickly note it because from 15 minutes we have noted it down. Noted, guys.
Yes, sir.
Then yeah, please put down this part and right. Otherwise, you guys should not quickly take a sketch because we'll get behind quickly. Yes, noted, guys.
1 minute. Can you scroll?
Scroll down.
Yes, sir. Can you scroll up? Yes, sir. This much.
Yes, noted.
Current screen.
And
Sir, can you scroll up it up?
is this okay?
A bit up. Yes, sir. Yes, sir. Done.
Done. This portion, right.
So 1 minute. Can you go a bit up?
Whenever guys have completed, we can proceed. Yeah, what is in here? So what we have done is that, so we have connected n EMF cells, right? N cells having EMF E and internal resistance R. So n cells in series. So this n is n cells in series. So we change this diagram to this equivalent diagram, and then we have one single cell, and all those connected are in parallel. So M single cell connected in parallel. So this is M. This is M. That is N and M. Is that clear, Shah? Yes, noted everyone.
Last.
20 minutes we have been to think through. Now, what I will do is that I will complete this chapter 1.
Yes, sir.
Yeah. Okay, so the next topic is RC circuit. What is an RC circuit? So we have this capacitor and this resistor connected in series with this cell whose EMF is so this is E, and this has a capacitance C, and this has a resistance R. So we know that this voltage will be divided in this one and this one. So E would be, and what is the voltage in capacitive circuit? Q is C, right? So V would be Q by C. So voltage in here would be Q by C, and we should write a small one. Let us write that Q, because this is a variable one, and then this is IR. So this is the equation, and the ultimate goal is to find out how Q is balanced. This is the question. So if we write this IR as dQ by dt, and then this is R plus Q by C, and this is so then we can take this R in this side. This would be Q by RC, and then this is E by R. Okay, so then what would be this? So we know that E is how much? So E is, let's say the total charge of this capacitor is Q. So E would be this Q by C, right? P is small q, so Q, and E is Q by C. So then we can write this as dq by dt, plus we write this RC as tau, right? This is some tau, and this is Q by RC, right? So Q by RC, which means Q by tau. So let us write it as this is by. Okay. And then, yeah, so if we take, so when we solve this differential equation, so this is a linear differential equation. So have you guys, yeah, so have you guys reached this differential equation? You guys have mathematics, right? Yes. Tarif and Shavez, you guys have mathematics, right?
Yes, sir.
So have you guys reached this topic linear differential equation? Yes. In homogeneous differential, no. So this we cannot convert in homogeneous differential equation because this is dq, right? No. Don't y is solved, right? Y is worry about. Yeah. So this is a linear differential equation because this is in the form of dy by dx plus some pxy is equal to some qx. So this is in this form. This is a linear differential equation, and to solve this equation, we calculate the integrating factor. So that part I will not do. I will just directly write that this charge would be Q 1 minus E and T by tau. So this would be the solution. And how do we get this solution? So you guys, yeah, integral P dy. Yeah, so that, oh, already you guys, so yeah, so integrating factor is exponential px dx, not dy. So px dx. So then we calculate the integrating factor, and then this becomes complete differential equation. So in this way, we calculate the integrating factor, multiply with it in both the sides. This will become complete differential equation. So then we'll get this solution, right? So you can see that what would be the integrating factor in this case. So that would be P is 1 by tau and dt. So that would be E t by tau. So this is the integrating factor. You multiply it with both the sides. This will become complete differential equation. When you solve this, when you write RC and when you replace E as Q by whatever C, so then you will get this. Yeah, so then you will get this, right? So this is the charge of a RC circuit, right? Charge of an RC circuit, and this is in the charging state. So this is in the charging state. So when you draw the graph of this one, right? When you draw the graph of this one, so this is Q, this is time. And initially the charge would be, let's say, initially the charge is 0, because if we take t equal to 0, so this is 1. So 1 minus 1 is 0, right? So in charging state, the charge would be 0 in capacitor. And then gradually the charge will increase and it will reach the maximum. So maximum charge is Q. This is the maximum charge, right? So this charge it will reach when it is yeah. So the graph of this one would be like, and this is Q. So at t equal to infinity, this will become Q. So this is called the steady state. So in a steady state, what will happen to the charge? So charge will become in the steady state, because t would be infinity. So t is going like this, and at t equal to infinity, this is minus infinity, so that is 0. So q would be q at steady state. And steady state, which means that it is approaching a constant value. So that is the state. And the current is dq by dt. So this would be d by dt of q 1 minus et by tau, right? And I have already told you guys that this tau is what? So this tau is RC, right? So tau is RC. Okay. So if we differentiate this, this is a constant term. This q is a constant. So this would be simply e minus t by tau, right? And we have this q, and this minus 1 by tau will come in multiplication, right? So this is when we differentiate this thing, so this will be Q minus and E minus T by tau, and then minus of 1 by tau. So minus minus cancel, and Q tau is RC, right? So this would be how much? E minus T by tau. So this is I naught. Okay. So this is the current. So if we draw the graph of the current, so this will be decreased, right? So this will, let's say at 0, so this would be maximum, and then it will decrease. So it will be like so this is I, and this is T, and this is I. But we have a particular time, right? So at t equal to tau, at t equal to tau, what will happen? So at t equal to tau, this is tau by tau, so minus 1, right? So at t equal to tau, the charge is q1 minus e minus tau by tau. So that cancels, and this is q1 minus e minus 1. So this is q, and 1 minus e inverse is 1 by e. So this would be how much? Q1 minus e is 2.73, right? So how much is that? Uh, 1 divided by 2.73. 1 divided by 2.73. So that is 0.366, right? And then this would be how much? This is 4, 3, and 9, 3, so 6. So 0.632. So at t equal to tau, Q would be this, and current would be how much? Current would be I naught by I naught E minus tau by tau. So I naught by E, which is 0.365. So that will be at t equal to tau. And then the case of discharge, right? So for the case of discharging, Q would be simply Q E minus T by tau. This is discharging, and current would be out. So Q minus of yeah, so E minus T by tau, and then 1 by tau. So minus Q by RC, right? E minus T by tau. So that would be minus of I naught minus T by tau, right? So that would be the current for the case of discharge. So this minus sign represents the current is moving in the opposite time, right? So yeah, this is the case of discharging, and then we have then we have this Joule's law of so Joule's law of heating says that the heat dissipated in the resistance, so that is equal to I square RT, and this is equivalent to V square by RT, or this is equivalent to VIT. And then we have this power dissipated, that is equal to this h by t, which is I square r, which is v square by r, or which is equal to by 2. So we generally calculate the power dissipated in terms of r, because this is fixed. Only I and v are changing. Only this is fixed. So we write the power dissipated in terms of this R. So always remember that. Okay. And then we have this bulb problem. So that is an important problem. So we have this bulb problem. So what is this bulb problem? So whenever you are given a bulb, right? So there are information which are given on that bulb. So there are two things. One is that the ratings are given, right? So rating of the supply voltage, rating voltage is given. That is V naught. Rating power rating is given. That is P naught, and it will have some resistance. The bulb will have some resistance. Similarly, you have this apply, applied voltage. So applied voltage would be P, and then you have this power dissipated on this bulb. So that is P, and again you have this resistance. So resistance would be C, right? So that is R. So you can calculate this resistance using this relation, that P naught would be V naught square by R. So you can calculate R by V naught square by P naught, or you can calculate the R using P square, by P. So we can calculate the resistance of the bulb using the applied voltage and power dissipated, or we can calculate the rating voltage and rating power. So then what do we calculate in the bulb problem? So we have combination of bulb. Combination of bulb. So first is a series combination. Let's say we have this series combination of bulb, and this is connected to some voltage supply of E and current I, and it has a rating of let's say V naught, right? It has a rating of V naught, and if these bulbs are similar, so its voltage rating would be similar. So it has a rating V naught, it has a rating V naught, it has a power rating which is P naught 1, it has a power rating which has P naught 2. So it will have a resistance R1, it will have a resistance R2, right? So R equivalent, that would be R1 plus R2, because this is connected in series. So series combination. Okay, and power would be how much? So power dissipated would be V square divided by this R equivalent, right? This is the total power dissipated. So this would be how much? This is V square and R1 plus R2. So how can we calculate this resistance using this rating? So we know that R1 would be V naught square divided by P naught 1. Similarly, R2 would be V naught square divided by P naught 2. So this would be V square and V naught square by V naught 1 plus V square. So plus V naught square and divided by V naught. This would be how much? So this is P total. And in the electrical appliances, right, in your home appliances, this applied voltage is equivalent to this rating voltage. So your in home appliances, this applied voltage is equal to, voltage rating. So that would be, so your P would be V naught square divided by V naught square. We can take common 1 by P naught 1 plus 1 by P naught 2. So this will cancel out. And if you reciprocate this thing, so that would be 1 by P. And this would be 1 by P naught 1 plus 1 by P naught 2. So in series combination, this is the effective power, right? In series combination, these two bulbs have these power rating. So effective power dissipated, total power dissipated with this, just like the resistance in parallel case. Similarly, in the parallel combination, power would be P naught 1 plus P naught. So if you have two bulbs connected in parallel, then this would be, so this has P naught 1, this has P naught 2. So total power dissipated with this. Any question up to this point, guys? Any doubt, any question? Tarif and Chavez, any question? Yes, Tarif guys, there.
Yes, so yeah,
Yeah, so any doubts up to this point?
yeah.
Okay, then slow down. Ours is please note down. Like quickly note it down because we have to do this Kirchhoff law and then yeah, so then only galvanometer, ammeter, and voltmeter will be remaining, so that we can quickly you guys note it down. And whenever you guys want me to slow down, so Yes, whenever you guys want me to scroll down, please. Yes, noted, guys. Tarif and Chavez, noted.
Yes, sir.
Then please, this part. This is the point at which t equals to tau. So we have calculated at t equal to tau. Q is 0.6 something Q, right? But at t equal to infinity, so at t equal to infinity, this becomes Q. So this graph is very important because this tells us everything. So initially, the charge is 0, right? Then it is charging, and at infinite time, at t equal to infinity, this becomes Q. So that state is called a steady state. At steady state, Q has become Q max, and current would become. Yes, whenever you guys have noted it down, please. Yes, noted. Tarif and Chavez. Noted, guys. Yeah, Chavez has noted. What about you, Tarif? Tarif noted.
Noted.
And the no. Yes, noted. Tariq.
1 minute. Yes, sir.
Done. Okay, then please note down. Yes, noted. Right.
So can you slow this?
Yeah, scroll down.
Up, sir.
Up.
So I think I missed a bit of something.
This part.
Yes, sir. Down. No, sir. Down.
This one. This one. Is this okay?
Yes, sir.
Yeah, so we can write this as positive because this minus sign only showing that this is the opposite term. This is I or the minus. Okay. So these parts are equivalent, right? So
Yeah.
always, yeah, always remember that we have to calculate this resistance. So whenever we are calculating the power dissipated, so we have to find out the resistance of all these things, right?
Then you say you'll stop fitting and this is the final formula.
Yes, yes,
So can you show your slow fitting and this is the final one?
just the final one,
Yes, sir.
this one.
Yes, sir. Can you show?
Yeah, so, and yeah, what were you saying?
So can you scroll?
Up. Oh, this
Yes, sir.
one.
Yes, sir.
So I'm skipping and going to the
Yes, sir.
done. Okay, so then what were we you noting down? These portion you have completed, right? Have you completed these portions?
Yes, sir.
Then these parts are right.
Yes.
Okay, so quickly note it down, and then only Kirchhoff law is remaining, and yeah, so this chapter is called as a media bridge. This chapter, and then in the last, moving charge and magnetic field will take only two classes. Then we have this AC electromagnetic induction that will take one class, and then we have this AC. My voice is little blurred. Okay, am I audible clear now?
But
Yeah, so is that clear now? Is my voice clear now?
yes, sir.
Yeah, so I'm saying that moving charges will take two classes, and then EMI will take one, and then we have AC that will also take one, electromagnetic wave also one. So then these would be complete. And yeah. Background voice is coming. Okay, some background voice is coming, so let me handle that. Yes, whenever you have noted it down, this is home appliances, right? Not done. Tarif, what about you? Done.
Yes, sir.
Then quickly note down this. So, yeah, in the next class, I will start this moving charge and magnetic field. But in half an hour, we'll talk about those whatever topic which is that will also. Yes, completed. What about you, Tari?
Yes, sir.
Done.